This is the Amp Hour Podcast, released August 21st, 2025. Episode 701, Electric Propulsion with Todd Bailey. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Todd Bailey from Starlight Engines, now Muon Space.
Hey, welcome back, Todd. 11 years later. This is a trend that I am slowly working through old guests and getting updates of where they're from. We just had another 12 years ago guest, and now 11 years ago for you. So you've been busy. You've been very busy.
I spent like 1 minute looking back on what it was that we were talking about then, and where I was in life, and it's a good 10 years or 11 years to have bookended. There's definitely stuff to talk about.
Oh yeah, definitely. And you and I have spoken on and off throughout that time. I think because you have family in Cleveland, I used to live in Cleveland, so we get to like hang out at Thanksgiving. I think that was like the thing I always remember is like you and I would like go meet up at a bar and hang out for a bit.
I looked forward to it. It was like a fun get out of my hometown and nerd out trip that I liked.
And then I had to go and move. I moved away, and then it was all. I came to New York. You're still in New York, and we got to hang out there. And it's been good to keep in touch, and really fun to watch your progression as an engineer and just like the stuff you're working on. Last time you were here, could you give us a quick glimpse into what we were doing last time? Obviously, I'll link in episode, what was that? 194 of the Amp Hour.
Yeah, I think that was 2014. Then I think at that point I was still a contract engineer, and I think that I still was largely working in my home lab, which frankly I still spend probably 90% of my working hours doing. Sure. But I had come out of Toy World, and I'd moved to New York City to build new media art for people, by and large. I built a bunch of electronics for a show in the Whitney, which was really exciting. And I think at that time I was building sort of like vanity robots for the rich and famous, which is cool. Like it's a great gig with a lot of good stories, but I think like at that point in my life, previous to that, I had been doing art stuff, and I spent many years playing in bands and largely working on musical electronics and synthesizers and that sort of thing. And probably around the time that you and I spoke was sort of a very intentional transformation from being somebody who was mostly interested in cool to
I was going to say you were one of the coolest guests we had. I mean, I knew you were cool because you were just you were this hip kind of dude living in New York working on art stuff, but also you're such a nerd, like unapologetically interested in Jim Williams and all the stuff that I was interested in. Like that alone is my definition of cool. Of maybe you're whatever you look like, but you're actually geeking out on the things you care about. Like that is that's the coolest thing you could be. But also objectively you were cool. In ways that I will never be.
I'll use a more derogatory term then. I was more interested in being like a hipster then.
Yeah, right.
Cool
in Brooklyn?
Cool,
no.
Cool is hard to pin down. I mean, it was too late. Sure. It's after the fact. It's already not cool. But
we're both dads now, so it's all over, man. It's there's no going back to cool. In that.
Oh
way,
yeah. No. There's very little. Yeah. Kids these
cool
days.
is gone.
So anyway, but I guess with respect to electronics, I had spent a lot of time building things for performance or for sort of out there stuff. The conclusion that I came to, and it was hard to come to because it required a lot of soul searching, is that I was considerably better at building musical electronics than I was at playing music.
Okay.
And so and part of you can tell, right? You spend all this time making a thing, and then for me, I would put it on stage, and you're it doesn't play itself. It's you still have to bring the magic to it, no matter how
you got to make robots or something, I don't know, synthesizers and need sequencers, right?
They do, and I did,
right?
but at some point I was like, well, what if what you really are better at doing is actually the electronics bit of it, and it required admitting that I wasn't as good at the other things. So there was like some self-reflection I had to do. So yeah, that was probably before I came to New York, and New York was like in the process of like sorting all that stuff out. I was still mostly working on art stuff, but other people's art stuff. And like fairly shortly after that, I got I knew a guy who also worked on artsy fartsy electronics, named Andy Raitano. And Andy worked at Lockheed Martin. And he was like, hey, you should come work at Lockheed. And I was like, mind blown. Like, I don't know, it's not very cool. But I was like, why not? Like, why not do it, right? Like, if it's true, if what you really are interested in is learning about the world of complicated electronics, like nobody, like working on a sonar system, which is what I did, is like, it's, if you've ever had to worry about an audio transformer, it's like the time where the specs in that transformer really matter. And like knowing that stuff, it's not like somebody arguing with you about like warmth or something like that. It's like, no, we could, the signal to noise ratio, is it what it needs to be?
Right.
And it was like, it was stupid not to. And so I did it. It wasn't what I wanted to do forever, but it was a good team, and it was not soul crushing, and it was like, weird for all the reasons that you might think it would be weird to go from that world like art world to defense world.
One thing I remember so we spoke about this when you were making this transition, I think, and I was very curious about it. And I remember you talking very excitedly about some of the gray hairs you got to work with. And like that as a guiding, like just for young engineers listening, like that as a guiding light, if that's the only thing that guides you, I think, in a career move, I think people almost always do well. I mean, obviously there's personalities and things like that can blow up there too, right? But just following talent of people to learn from, and like having the opportunity, like Andy, like opening that door for you to walk through, like that alone is going to do people a lot of good, I feel like. And like, whereas I'm not sure it's followed all that, it's not like promoted all that much, in popular culture.
Yeah. I think I have come up with this sort of rubric for what a good job is at this point now. I've had many more jobs since then. And, a good job should do, there are three things that I think you can get out of a job. And this is all, again, this is like, grain of salt. This is coming from a place for somebody who's relatively late in career and has a lot of choices and opportunities. And if you're just starting out and you need to pay your bills, like pay your bills. But if you,
eating is important.
A job, in my opinion, it can be fun. It can give you enjoyment. It can be lucrative. It can give you money. And it can teach you something. And for a job to be worth pursuing, I mean, again, caveat, pay your bills. But, for this point, for a job to be worth pursuing, it should be two of those things. And ideally, it should be three. It's hard to do that, but like,
well, there's shades of gray for all things like lucrative too, right? It might be like, bottom of the pay, like bottom 25% percentile, right? Might not be a lot of money relative, but it might be enough, like that.
Yeah.
Right.
Yeah. My first like technician job was like, it did not pay very much, but I was like, I'm rich. So you're right. It's absolutely relative.
Okay.
So yes. So, I would say my whole career has been sort of like, at some point has been like, where can I go to learn a new thing? The more esoteric you get, like the weirder the stuff you worked on becomes, and the more specific it gets, the harder and harder it is to find some sort of figure that knows more about it than you.
Yes, right.
And so at some point, if you can find someone who is smarter and better than you should do that. And if you can't, then it sort of becomes, the onus is on you to find a project which will force you to learn new things.
Yeah. And I do think there's always the side thing. So like in the example like we're talking about with the Lockheed thing, I'm sure you were working with like 30-year experts in sonar. And some of those guys have probably been doing that their whole career. And would continue to, like there's the pigeonholing problem, of course, as well. So if you're trying to sample these different expertises, I don't know, you might have to pull the lever and get out before you become the new 30-year expert, unless that's something you find out you really, really do want to do, and keep making sonar only for 30 years, right?
Yeah. The thing about that job that was valuable was there were certainly sonar experts, but sonars, there's a lot that goes into it. So there were a lot of people who knew like the system level trades of how you make a navigation sonar, and there were people who knew the algorithms and Kalman filters and and how the ocean works and that sort of thing. But there was a finite number of people who were good at electronics, and so that's how I got in there, because they're being like, all right, well, we need this signal to get into the FPGA to run this transform on, but man, sure is annoying to get that signal in there. So
don't you just hate analog? And you're like, no, I don't actually.
Yeah, I mean, that's how I got to do that. Like, I got hired to be to build some test equipment for them,
Cool.
and
Cool.
It was an equipment rack that tested something. But I spent a lot of time in the lab. Couldn't keep my big mouth shut and was like, "Wow, looks like you're getting some. Oh, that's underdamped or whatever." And if you poke your
and
finger,
you do it better. You do it better, son.
Yeah, I mean, it really was like that.
Yeah.
And at some point, I think I came back and built some prototype. So I absolutely came back and built a prototype circuit here and like dragged it in, and they were like, "You're crazy," but yes, okay, you can work on this thing.
What about getting over that hump? You obviously had all this consulting experience. You had your portfolio included very technically complex things, but was not a traditional portfolio. You kind of talked about this, I think, before we started recording, as like a bona fide, but getting over that hump for like Lockheed HR, was that Andy that did that? Again, just thinking about the people that are listening that are not in that space yet. How did you get over that hump?
I mean, I will say this. I think that probably every single job I've ever gotten, and there's maybe an exception in here somewhere, has come from knowing another human being. Even like at the very beginning. Actually, my first stereo repair job out of college, my first job out of college was repairing stereos. And I got that by answering an ad in the paper. But I think every other job I've gotten since then has had to do with like just shooting the breeze with people who do similar things to you.
Yep. Yeah.
So yeah,
also
in that
known
case,
as networking, right?
It is. It's networking, and it's like, I don't know, man. There's a million things to be good at in life, and nerds historically, like, are some degree of antisocial, and it really helps to just like, you don't have to compromise yourself. Like the Andy Raitano was a buddy because he was into the Sega Genesis, and we both liked 6502 programming. That networking was not like forced in any way.
Right, exactly. That is like-minded, and just happened to be his day job was very beneficial to your career path as well, right? Like, but you're still buddies. Didn't you guys? You talked about that last time when you were on here too. You guys built your own, like a VEC 9, right? That was who you worked on with then.
Yeah. It was actually, I think everybody who worked on that project, almost everybody who worked on that project worked at Lockheed as a day job. So there was another programmer named Mike Dooley, who also worked there. My friend Mike Schmidt, who I worked on, Calvin Klein's robot doors with. We got him a job there too. And so it was just like, all the cool kids like showed up and like worked on sonars and then made games about the Soviet Union, which we, amused us no end.
Yes, that is pretty good. Yeah, and there's a little callback nugget in there too. The robot doors that Todd was not allowed to say last time who it was for. 11 years later, he could say it was Calvin Klein. Hamptons. Yes, so that's episode 194. People can go and listen to that for all the details on that. Well, not all the details, but a lot of the fun stuff in there. So that was good.
Yeah. I learned about ground loops and conformal coding and all kinds of things on that job.
I do remember. I was thinking about that as I was like spraying down boards one time. I was thinking about Todd having to deal with salt spray from the ocean. I do remember you talking about that.
Oh yeah. Conformal coding is actually still a significant part of my life these days.
Yeah, exactly. Yeah. Well, we'll get into that for sure.
Yeah.
Yeah. On the Lockheed thing, you were starting on the test stand, then you started moving your way into the space of like more design of the stuff.
Yep.
How did that? So I guess first off, how did that work with clearance? Like, was it like, did you have to like go get cleared, or did we already get cleared before that? Okay.
I had to get clearance.
Yeah. Okay. And then like, what is that like? I guess. I mean, I don't know.
What's it like to get cleared?
No. I know that part. I've given people references before, but what is it like then? Working on something that big and kind of important. And kind of like we've only had a limited number of kind of military guests in the past.
I see.
Yeah.
What's I suppose so interesting is the electrons don't know it's military, right? They follow all the same rules that they always follow. You expect all these people to be like weird jarheads or something, and they're not. Like, they're all people who are motivated by the same things that you are largely. The team, especially the olds who were at Lockheed, like the people who were 20 years older than me, were great. Like they had been there for a long time. They were a different like generation of engineer who had like a career and stayed at the same place for a long time and like
Mhm.
had like loyalty and like all the stuff that like young
Like, yeah,
people
company loyalty. I mean,
company
yeah,
loyalty.
sorry.
Yeah.
Yeah.
Whether it was warranted or not, which often it wasn't,
Mm.
but to my opinion, but like, but no, they were like, they were sincere people who really cared about what they were working on. Probably the biggest sort of like the biggest transition, I guess, was for those of you who've only ever worked in like cool hacker world, there's a lot of in like more legit world, like requirements driven design
Yeah.
is very much a thing. And the first time you encounter it, you're like, this is so stupid. Like, why are we setting out to like have this big dumb spreadsheet of stuff that mostly doesn't matter?
Yeah.
Like,
Yeah.
and getting your head around that at first is annoying. And then at some point, if you're me anyway, I'll speak for myself. Like at some point, you're
Sure.
like, actually, it's kind of the only way to start a design that matters, right? Like, what's the point? It's like it's another way of
Mm.
being like, what are you sitting down to even do, guy? When you sit down and work on this thing.
It's done kind of ad hoc, a little bit more ad hoc in a consulting context, right? As well, where it's like usually if depending on the customer, if the customer has a set of requirements, you're going to do that. But if it's
Right.
like Calvin Klein calls you up and says, "I want robot doors," you have to go and
Yeah.
like figure out what the hell does that mean.
Mm-hmm.
Anyways, right? Like you're part of that product side of things versus like delivering the thing that's on the spec sheet.
Yeah, exactly. And I would say, of the things that matter, like going in with an extremely clear set of goals. Like I remember there was an older engineer named Joe, and Joe was great. And is someone I still keep in touch with. But I remember building this circuit as well as I could, this, you know, sonar related circuit, and like going in and being like, look how awesome this is. And Joe like took the same data that I had and then put it in a graph and then overlaid it with another graph and then was like, actually, here's the error in your circuit. And did this
Yeah.
really like not very hard to do analysis. And I was like, mind blown. Like, whoa, that's what I should be doing the whole time. Like I wasn't rigorous about it. And then I was like, oh, I've got to learn how to do that. And I guess starting from being like, what's the point of this circuit or this project, is valuable in that it keeps you from focusing on stuff that doesn't matter, right? Like it's easy for engineers to get hung up on things like efficiency and accuracy. And often those are great things to focus on, but sometimes it doesn't matter. And spending a bunch of time on a part of a design, which is not the most important part of the design, is detrimental to the project as a whole.
So you're almost saying in the converse as well, right? So Joe is saying this isn't spec'd well enough, and it's measured, and you could say this is specifically not spec'd well enough because it doesn't match the graph, and here's the error. Mm-hmm. But you're also saying in the other direction, you could over-engineer it, you could overdo it, and you might be wasting time, wasting energy, wasting resources that you were not actually being asked for, and that you should just move on to the next thing.
There's the done is better than perfect,
totally.
which you're getting at with that. But there's also the if you have extra cycles as an engineer, that's great, but focus on the thing which is going to help the system. Like instead of making this thing hyper accurate, maybe make it like have fewer parts or be more maintainable, or have more test points, or like something which isn't which is also useful, but it's not the like it was 12 did a 12-bit accuracy before and now it has 12 and a half bits, like and the requirement is 10 bits, so that's great, but like that's not really like you are just kind of screwing around right now.
I have not had a Joe in my life in a long time. But I do have the consulting forum that I run, and I find that on there I've had similar kind of like levels of like the need for rigor, and especially in a vacuum, right? Like when nobody's looking over your shoulder, when nobody's asking you to do that chart overlay, right? Like nobody's asking you for that data because there's no one above you. It's like that's actually when it matters the most, I think. It's like you're almost like proving it to yourself and building that habit that you're talking about. Like I'd be very curious where Joe got that from, because that's some hard-won knowledge, I feel like. And Joe probably also had a Joe, right? But like if you don't have that and that rigor, it's or that example, like positive examples of it, it's it's hard to come by, I feel like. So,
Yeah, it's true. And it's cool. It's cool to like watch younger people heading down that same path and to like, smack their hand and be like, actually, you can save yourself a couple weeks if you just look at this other thing now for just a minute.
Yeah. I am curious, but later on we should circle back to when I'm curious about your mentoring of people now that you're years on. Well, okay, so you were at Lockheed.
Yep.
I remember another bar conversation with you. And I remember, and maybe this is apocryphal, and maybe this is not actually what happened, but I remember you talking to me about space, and you were interested in space.
Yep.
And I remember you and I spoke about Zephram Cochrane.
Totally.
And I wanted to bring that up specifically here, because I always think about that with you, especially given what we'll get into. Todd works in space now, just as a spoiler, I suppose. But but Zephram Cochrane is something that came up between us, and I don't remember why, but I think you had said you want to be Zephram Cochrane.
Oh yeah. Not apocryphal at all. I accurately remembered. Yes, I want to be Zephram Cochrane.
Okay, so now we should probably explain who Zephram Cochrane is. He is actually, why don't you explain who he is? Because we both.
Sure. In the I am a big fan of science fiction. I have strong opinions about it.
As am I.
Lest this go down, like some forking path. I'm a big fan of Star Trek generally. Because mostly like for a million reasons, but ideologically, like I am into Star Trek. Like Star Trek paints a future which is like it's not grim, which is cool. And there's a lot of things I like about Star Trek. In the world of Star Trek, Zephram Cochrane is the engineer who figures out the human engineer who figures out how to make warp drive. For humanity. Other people in the universe have figured out the warp drive as well. But he's the one who like takes Earth's civilization by dint of engineering and makes it into something which is valid across the galaxy.
Yep.
And Zephram Cochrane is also like DIY. That's the other thing too.
Yeah, and the warp signature. So this is in Star Trek Generations. I think they have him portrayed, and then in the earlier one as well. Mm-hmm. But that's kind of the idea, is that he's the one that kind of drags people into the future, right?
Right.
That's the idea. Yeah. And so you're making warp drive of some sort. We'll come back to that for sure. But I remember you talking about that, and then you were saying that you're trying to get into space, right? You were already underwater, somewhat space-like, but then you were trying to get into space. So then, yeah, I remember that, and I think we had talked about who you could maybe talk to, but I think you did make a transition over to a space. Was a startup
actually?
At that point?
Are you the one that made that introduction
to Sean?
To Sean.
Yeah, I was. Yeah.
Oh, well, thank you. You're the reason this all happened.
Well, barely. Yeah. Yeah. Sean.
Meehan.
Sean Meehan. Of course, past guest of the show. Sean was at what was at that time was a. Oh, he was at Planet, and then he was going to a startup, I think, or maybe he was already at the startup. So when Sean was on the show, he was doing robots after having left Planet or something like that. I'll link in the episode. And yeah, so you talked to Sean, and that's how you got kind of moved over to space, yeah?
So the company was Astra, and at the time they were stealth space startup, which they were for many years. And there was about 30 people. And look up Astra if you are curious. There's a Netflix special about them now.
Oh, is it really?
How wacky they are. It's called Wild Space. There's also a book about it.
I remember there were some other names there though too that have been on the show. So Charles, I believe.
Charles Aylward, a great friend and a fine engineer. Yeah.
Yeah. And actually, Charles is one of the people on the forum that I was talking about that I think about like the level of rigor, and like he's top of that list. You and him talking about this sort of stuff is like, making sure your stuff doesn't blow up. Real important. And I think maybe Jerry was there for a little bit as well.
Ellsworth? Yeah, she was.
Yeah. So lots of familiar names to people on this show. So that's good.
Oh yeah. It was my first proper Silicon Valley startup experience. It was my first foray into commercial space. It was crazy. That was a crazy job.
And it was early in the commercial space kind of stuff too, right? Like Planet was like one early one as well, but like in terms of like launch company, it was what the second one I thought of after like a SpaceX kind of thing. I thought
Yeah. So forests have fallen about like the history of commercial space, and there's
Yeah.
Wild Wild Space is a good one. There's another one.
Okay.
It's based on a book called When the Heavens Went on Sale, which is by this guy who wrote a lot about Astra and a bunch of other stuff like that. It's got early history kind of stuff, which is cool.
Got
But
it. Yeah.
I think a refresher is sort of like, space for a long time was not like commercial space meant bigger companies, right? Like Boeing or Maxar or companies that built large satellites and or large launch vehicles. Design cycles were relatively slow. The number of spacecraft in orbit was relatively low compared to today. Really, for better and for worse, the company that really, opened Silicon Valley's eyes to the potential of commercial space was SpaceX. There was a group, I want to say out of maybe JPL. There was an old Air Force guy who had a bunch of, youngsters under his wing, and that's what sort of Planet came out of. So I think SpaceX was first, and then sort of the first generation of like commercial space companies included Planet and maybe some other companies. And I would say Astra et al. Were like the generation following that. And as far as launch vehicles go, obviously SpaceX was first, and then I would say Rocket Lab was second. And then when I started at Astra, I was like, the good engineers, I think should always be a little bit glass half empty. And I was like, I can firmly say that, we're in third place, which is not that bad. And it's, but like we can do it.
We can do better.
Yeah.
I have the chart that says we could do better. Here's our error.
Well, okay. So, not to get into it, but like, yeah, all right, I'll get into it. So like the thing about Astra that was a wild experience was it was like the early days at Astra were very much like, we have these problems, we need to solve them very quickly. Here's a credit card, come back when the thing is done.
Wow. Okay.
It was empowering because it's rocket, right?
Right.
It's a great environment for learning quickly. It is a good environment for examining what is important and what is not important, because like speed is such a deciding factor, right? It is a good chance to like fail on stage a little bit in a way where like you're gonna mess something up, in a way that like everybody in the company sees it and it costs like $1 million, and you like, that's you did that. Todd Bailey did that. He cost the company $1 million. TOD,
and you're saying
he's right over there, that's him.
But you're saying that's a good thing. That's what you said, is failing on stage is a good thing?
It is an uncomfortable experience. And it is
so it prepares you maybe for other things that might be big, maybe.
If that's a world that you want to be in, it's a useful experience to have, because there's kind of you can reduce the chances of that happening by making good decisions, like slowing down when it's smart to slow down sometimes, but there will always be a possibility for it happening. And generally the faster you go, the more likely it is to happen. All of these companies, at least as of 2025, everyone that I've ever worked for, prize is going quickly, which means that you will make terrible mistakes and you'll have to recover from them.
Got it. Just as a frame for, I guess I'm getting older. I'm thinking more about the people, young. We don't have a ton of young listeners. Ton of young listeners have entered Todd's lab as well.
Yes, this is my daughter. That also happened in the last 10 years.
That's right, exactly.
Can you say hi to everybody? Say hello. Are you eating Cheerios?
Hi.
Hello.
Can he hear me?
He can hear you.
I can, yes.
So will a bunch of people who are listening to this episode.
That's right, yeah.
Nice to meet you.
Nice to meet you, yeah.
Kiddo, you mind if I go on with my long, boring daddy story?
Okay.
All right. Thank you.
Bye.
Bye. Yeah, I think about that, that younger crowd and just how it would this be a thing that you would actually tell people to run towards, right? Is like failing on stage a thing that you would tell them to run towards?
What in particular? Commercial space?
Failing on stage, like that as a thing to like go after.
It depends on what you're going for in life. Right, like I think probably a couple years ago, it would have been like, yes, you must learn to fail in embarrassing, terrible ways and eat your greens, and there are different people who are into different stuff in life. I think what you really want is to build hard things. One of the ways to do it is to do it in a commercial sector. If you want to do it in a commercial sector, then yes, you have to learn that lesson.
Well, that's good. Yeah, then that's a thing people should seek out and maybe go towards, and that's important then. Yeah, okay. How often did that actually happen though? Like, was it just the fear was there, or did you actually cost $1 million?
That was sort of an example I gave. No, I mean, it's things we built totally did blow up sometimes, right? And it was expensive and cost a lot of schedule. They were unmanned rockets, and safety is one of those things that people take pretty seriously at a company like that. So largely it was just schedule and money and not people.
Got it.
The hardest thing that I probably maybe have ever built, I built at Astra, and it was the motor control electronics for the booster stage engine of that rocket. So if you're a rocket nerd, you'll know that like booster stage engines are typically use an oxidizer and a fuel. They're usually liquid, and they're pumped into a thrust chamber where they are combusted, gas expands, and you make thrust. In most rocket engines, the pumping happens using turbo machinery, which is mechanically spun. So some of that propellant is burned, or some of the exhaust is used. It spins these pumps. The pumps pump fuel and oxidizer into a thrust chamber. Astra's rocket and Rocket Lab's rocket, at least Astra's at that time, used what they called an electric turbo pump, which was an electric motor that pumped fuel and oxidizer into the thrust chamber. And so early on, my job was building like the power electronics. Like somebody was like, I got hired to be an embedded programmer there, actually. But then they were like, you know what an op amp is? And I was like, indeed, I do know what an op amp is. And they were like,
do you know what an op amp is? When it's vibrating back and forth very, very quickly.
They were like, you're going to be the power systems guy. And I was like, all right. And they were like, have you encountered batteries? And I was like, I mean, hundreds and hundreds of times, but they were all AA batteries, and they were all in Barbie dolls. And there's some overlap there. Discharge curve is like still a thing.
Transistors, I'm sure, were involved in some way.
They were. So I had built a bunch of battery management system things, and then those got done. And then this pump motor controller came up, where Astra was making a booster stage engine. It was called the Delphin engine. It was a great engine. I have many issues with that. There are many complicated things about that company, but that Delphin engine was a good engine. And so it was my job to build the power electronics, which ran the pumps. And it was really hard, right? You had two different fluids. One of them was cryogenic. So like motor feedback was really hard. Like if you couldn't put Hall effect sensors on them, you couldn't, you could use an encoder, but you had to be really careful about how you did it. It had to be a really fancy encoder. And at the end of it, we made a 40 kilowatt, 500 volt, 30,000 RPM sensorless motor controller, that ran on batteries, and it was really hard. That thing was a challenging circuit. And I think probably the lesson, and this maybe goes back to requirements, which, God, if like this ends up all being about requirements, I'm going to feel like the lamest dork. But
no, it's just an offset. It's like the universal balance of like how cool you were in the first time we recorded. And now it's like Todd, the spreadsheet guy.
But the thing about it was, right, that was like, we made a great electric turbo pump in my opinion, which was deeply biased. But and ultimately it didn't matter, right? It didn't matter because the reason why it turns out people use mechanical turbo machinery all the time is over some size of pump, it's actually more efficient. Like you don't have to carry, an electric turbo machinery. Electric turbo pump is physically smaller, but you have to carry all these batteries. And once it's more than a certain number of like watt hours going through those batteries, the batteries weigh more than any pump you're ever going to run off a gas generator. And so we built this thing. It was fabulous. It got used for a handful of Astra's early rockets, and then they're like, we can't use it anymore. Because we fundamentally, the launch business does not want a rocket that is this size class, and we need to build a bigger rocket. And if we're going to build a bigger rocket, these pumps don't do us any good.
And there's some context, I think, in there as well. But Astra was trying to do like smaller payload, smaller size rockets. I remember they launched out of the desert, I think, didn't they? Instead of like
early on in the desert. Early on, they tested in the desert. They tested a Naval Air Station Alameda, which was awesome. It was an indoor test facility. Like that was another cool thing that Astra worked out is they got an unused naval base which had indoor engine test facilities, which is cool. Unheard of. And so they had these amazing test cells. So they tested there a lot. And then the early rockets went out of Kodiak, Alaska. So I would go up to Kodiak, Alaska with the rockets and get to.
That's cool for its own reasons, huh?
It was great. I mean, it was a fabulous experience.
What was the scale of these rockets when you were, like from start to finish when you were there? What were the sizes of them as well?
They were meant to fit in a shipping container, so
Okay. Okay.
they were pretty small by rocket standards. I can't remember the exact dimensions, but like
Okay.
I don't know, like a couple meters in diameter maybe, and
Yeah.
I don't know, 50 feet tall. Not sure.
I think shipping containers are 20, 20, 40 for feet. I think.
Okay, that sounds right.
Yeah. Incorrect on 2 out of 3 counts. It's 8
But I mean,
by
the lesson there
8.5
was like
by
it didn't
variable
actually
amount, 10,
matter
40.
how good the circuit I built was.
Got
Like
it,
it didn't.
got it.
It was like I could have gotten another 10% efficient. I could have made the best one the world has ever seen, and it didn't
Right.
matter. And it was like it was a sobering thing to learn, which was like good engineers don't build bad circuits, but all the time they build the wrong circuits. And
So this is kind of going back to the requirements thing then too, because it
yeah,
was like
a little bit, or it's
Yeah.
just being like it's not. Sometimes it's not how you build it or how you. It's not how you build it. It's what you build. And so like to make that decision, it's like you have to kind of go back up a step from being a circuit designer and think about like what's the problem you're trying to solve in the first place.
so like system design versus specifics. Like
Yeah.
system design is a critical piece because there's so many interwoven pieces there too, and that almost sounds like a business requirement as well of like just the scale didn't fit the market like
And
the
and
actual
for
thing
me,
that you
like
needed.
it sort of comes down to being like the point of making one of these things is to see it work. Is
Yeah.
to if you build a thing, you want to see it fly, right?
Yeah.
And so the goal is to get it to fly. And if you don't, yes, system level design matters, and yes, you can't sustain a business that doesn't have a product that people want. But also your project will never go anywhere. Like you have to chart a path where this thing that you brought into the world gets used for the thing that you designed it for, and therefore all these other things do have to be right, or it's just going to languish on your bench forever. And so if you really want your thing that you made to go out into the world, you need to see that path for getting it there. So like, and with that comes system design and finances and stuff. But like you want to build a warp drive, you got to find somebody who's going to buy that warp drive. Otherwise it's going to sit on a page forever.
Yeah. Right.
And that's like, it's all sides of a coin, but that's how I think of it. If you want to see it go to space, you gotta make a thing that can go to space and that somebody wants to put in space.
So this is almost like the ultimate version of is good is better than perfect. Like perfect would be the best circuit on your bench, but good is the circuit that makes it to space. Yeah.
It's the one that gets to space that counts, right? So it's the best
Right,
one that actually goes to space, which is usually
right.
nothing goes to space. So often it's the only one that goes to space.
Got it. Yeah. And then you really find out what's wrong with it when it goes to space, I'm sure.
Hopefully you find out most of what's going to go wrong with it before it goes to space.
Yeah. So before we go into the other, so you kept going with space, right? Astra was a thing, and then you went to other companies, and I'm just pinging down your LinkedIn, of course. But one other thing that was very interesting to me was that you were working remote for a lot of this as well, right?
I was.
Yeah, so that's also very interesting. Like, how did that work? Because I'm guessing that even with a shipping container, they probably didn't ship one to New York. I'm guessing.
No. I mean, I had
Not the whole thing.
I had a pump motor controller here.
Yeah.
So I have many things to say about that, but I'll try and keep it short. I think even probably in the last interview I had with you, the home workbench was the thing that I very much believed in. Jim Williams has an essay about it,
Of course,
called "There's No Place Like Home." You should all go read it. I have always believed in having your own sort of work setup, and there's a few reasons for it. One of them is there are people who are like, I like to get away from work, and I happen to I've chosen a career where I love this stuff, right?
It shows, Todd. It shows.
Being able to sit down on a weekend or whatever, to walk across the room and work on a thing is valuable to me. It turns out it's also really helpful for your career if that's the thing that you do as a job. So 2 things about remote. It's now pretty common. It was less common then. Early on, I think a lot of those companies thought I was going to move. So they'd be like, all right, well, we'll start this way, but eventually you'll see how wonderful the San Francisco Bay Area is, and certainly you'll come here. And that didn't happen. And there was tension for sure because of that. At the time when I started Astra, I did not have a child. My daughter was born while I was at Astra. And so then it's like a question of like, my partner has a career, which at the time was based in New York City. And I had moved to New York City. I liked New York City. I had a great workbench. I had a, kid. It required pushing back to be able to continue to work in the way that I was. And it usually also requires sort of a willingness when things are on fire to drop what you're doing and travel. So,
That's right.
having this home lab allows you, when your head is down, when your job is really like just being an engineer, sitting there and making simulations and tinkering with circuits on the bench, being alone in a room is actually fabulous. When you build this thing that's part of a bigger system and you can't test this 40 kilowatt, motor controller, I could do like a good like kilowatt, 1200 watts in this tiny room, but like, not 10,000. Testing the system, like if something was wrong, you were like, no, this is the reason I get away with like, being able to be a precious princess about, getting what I want, is when the thing doesn't work, then I show up and you spend like 10 million hours like under the rocket, like fixing it until it works. And then you leave. And so you have to give people enough faith that you'll actually do that. Conversely, once you've done that a couple times, they're loath to fire you. So you can get away with more stuff.
Yeah. So it's basically building trust, building relationships, that sort of thing.
Yeah, totally.
It isn't, I mean, it's interesting, especially because I can't think of many more, kind of like physical things than rockets, right? I mean, like rockets are like, I can ship tiny circuit boards with Bluetooth chips on them just about anywhere, but yeah, rocket parts are bigger and, but it's all still gets down to tiny silicon transistors in the end anyways, right? Microcontrollers, whatever. Okay. So then you left Astra. You went to a couple other rocket companies. What did you get to work on there? Why did you move? That sort of thing.
So after Astra was over, largely part of the Astra thing was that Astra was like, hey, really, really want you to come be here in California. And I wasn't willing to do that. And the other thing too was, that motor controller wasn't, it was a whole lot closer to done. It had been through several revs. It was like working. And I have learned that did you see the new Top Gun movie?
Yeah, of course.
I really love that movie. But there's a lot of old guy stuff in that movie about, Tom Cruise is like, I'm where I belong. And it's silly, but it's a little moving. And it's one of those things where I'm like, I know I am not going to be the happy, positive, productive force that I need to be for someone for whom I'm working if I'm not actually working on circuits some of the time. So like, it is fine to be a team lead. It is fine to help people to learn. But if I don't have my hands on a circuit board, some percentage of the time, it's not going to be a thing I want to do. It's going to be a thing that starts to build resentment. And typically with a lot of these jobs, like you sort of have to fight to keep in the trenches.
Right. They want to push you up into management, manage all these people, do all this stuff, use your expertise, that sort of thing. Yeah, totally.
And you have to be like, no, I am not going to do that. And sometimes that means leaving. Yeah. So I built the motor controller and I didn't want to move to California, and I knew that I liked propulsion. At that point I had spent a lot of time thinking about power. And that was like my, biggest, that was a real like drink from the fire hose like experience in getting into power. Like I would have said that I was into analog before, but like not like RJ theta like kind of stuff too much.
Right. Did you have a favorite transistor after that and you didn't before that? Is that kind of like,
well, a transistor is so complicated. So it's like, there's like, different strokes for different folks. It really is true. Like I'm a big fan of GaN at this point. Like I use a lot of GaN these days. So yes, I do have opinions about transistors as well as Star Trek.
Yeah.
But like I use a lot of BJTs these days. Like I use a proper bipolar junction and NPN transistor, which is great. It's like it's like all those synthesizers mattered because I get to make this like blob of BJTs now sometimes. But so I went to a company after that called Rocket Lab, who also makes rockets. At the time, they were starting to build. They had a third stage of their rocket, which they called a kick stage, whose job it was to deliver payloads into a precise, somewhere precise in orbit. And they had this concept that they could take this kick stage and they could make it something which would reside in orbit. It would be a proper like transfer vehicle or something that would support a customer payload. And so that became what is now known as Photon, I think, still known as that, which is Rocket Lab's sort of like satellite delivery vehicle. And to get the kick stage, to turn the kick stage from the kick stage into Photon, it had to have all these electronics that would allow it to survive in orbit. Largely, that had to do with power again. So like it was solar array stuff. And so I got hired by Rocket Lab to do that. But they were like, hey, if you get that done though, then you can. I knew at the time, like I went through the same kind of search when I left Astra to be like, all right, well, now you know a little bit more about space. You definitely didn't. You definitely didn't before. You didn't know what you didn't know. But now, looking at what's out there, if you want to do complicated electronics in space, what is out there? And generally, it meant like payloads, like sensor systems or radios.
Okay. Like
and
sensor talking back to the Earth kind of thing.
Yeah, and I love RF as much as the next person, but it's never been my thing. Sensor systems are hard because there's just so few of them. Like most of the commercial stuff that's up there is either Earth observation or it's a radio. And so that leaves power, which is like a huge problem. And if you're into propulsion and you're into power and you're an electronics nerd, electric propulsion is like naturally like comes across your mind. You read about it. You're like, wait, you shoot a giant ion beam out of the spacecraft and it pushes you around. That sounds like something
you know who else did that? Zeph from Cochrane.
well, actually,
yeah.
I think in the Star Trek parlance, that's impulse power.
Sorry.
But anyway, I learned about EP and I knew I wanted to get into that.
And EP is electric propulsion, right?
Electric propulsion.
Got it.
And Rocket Lab was like, well, hey, we're going to need that for our spacecraft. And so you can build that after you build these power systems.
Oh, the dangling carrot.
It was the dangling carrot. And they were like, you'll just, crank out this satellite power system in like 5 minutes, right?
Did they say, but you also have to move out here in order to do that? Because that's sometimes how they also dangle carrots.
Well, you know what happened right around that time was the pandemic.
Everybody goes remote.
Well, and it was actually really cool because it shut down everybody's electronics lab except this one. And all of a sudden, like being able to work in this lab started to be a bonus. Otherwise, I suspect probably the same thing would have happened. But at the time I was like, no, I can like build stuff here and like debug and run my solar array simulator and, get you this data. And so it was valuable. And so we got it done. We got the power systems done and they flew and that was cool. And during that time, again, Rocket Lab did some studies where they were like, well, we have this, I think it was a hydrogen peroxide motor that already works for the kick stage. So, if you do the trades and like what it takes to get to orbit A or orbit B, we could develop EP, but actually it doesn't serve the mission quite as well. And it's like going to take many years. So why don't we just use the engine that we do have? And it was one of those things where I was, medium mad because I wanted to build EP, but it was also 100% the right decision.
Yeah, this goes back to the spreadsheet thing, right? This is like that's done, and it works, and it. Oh man.
Yeah. So I was like,
damn it,
that's great. That's no, I agree, but I'm gonna find a new job. And so I did, and I worked for a company after that called Apollo Fusion, and a woman who was on my team at Astra was actually at Apollo. Her name is Alex Zanos. She's a great power electronics engineer. She's at Harvard Business School now. She also was like, I don't know. I gotta chart a new path. But she should
be running something soon, I'm sure. It sounds like
if she's not already.
Right.
So I saw that she was working there and I pinged her about it and she was like, no, man, this place is great. Apollo Fusion started as a fusion company. Then, fairly rapidly, they were like, oh man, it's challenging. They were like, we may not solve fusion in the next 6 months. And
it may be 50 years away. Not that kind of fusion. Yeah. Is it? Wait, so, and fusion, yeah? Is that right?
Fusion. Yep.
Like, okay.
Yeah, I think it was like a beam on beam fusion concept.
Got it.
To the credit, Apollo Fusion was very important to my history as a person. One of the reasons is the guy who is the CEO of Apollo Fusion is this guy, Mike Cassidy. Mike Cassidy has founded and sold many, many companies in Silicon Valley, and he's a very shrewd CEO. And this is before I joined Apollo. They were doing fusion, and after 6 months, they were like, "Man, isn't this kind of hard?" And Mike did what he do, and he was like, "All right, if we're not going to solve fusion, we have, this much money left, and this team of dorks. What are we going to make that will make this company profitable? And they were like, oh, we have all these people who know how to make ion beams because you had to make ion beams for fusion. What could you do with an ion beam?
Wow.
And so then they were like, oh, well, we could make a Hall effect thruster. And so they became an electric propulsion company.
In your head, when you read stuff about like Silicon Valley and they start talking about pivoting, do you think about the Friends episode like I do, with like Ross talking, like getting the couch around the corner? Pivot. They never make that connection from my head. Anytime I hear about pivoting in Silicon Valley, I go straight to Friends. I don't know about.
I mean, there's so much that's so. This is like, there's so much that's so cringy about Silicon Valley.
Yeah.
But it's like, I could go on for a long time, but in this particular case about...
Well, there's a documentary about it. It's called Silicon Valley.
Yeah, too close. It's too close.
It's too close. Yeah.
So so anyway, Mike was like, all right, we're going to make Hall effect thrusters now. And they did, they built a couple different iterations of thruster. And when I was interviewing, they were like, you know what we should think about doing is get some power electronics for this. Because... like, again, not to be all systems-y about this, but like, somebody who buys a Hall effect thruster is a spacecraft manufacturer. Usually they're like trying to put some antenna or some telescope in orbit. And that's what they really care about. And they need in order to close their mission, they need their spacecraft to move around. P.S.
Got it.
Space in our world, when you say spacecraft, what you pretty much mean is satellite. And they actually do say spacecraft. It's not to make it sound cooler. Sure.
Okay. Well, and just as a real quick break, can we talk about? So we've said third stage as well with the kick thing. So to layer it up. So stage one is the booster. Is that right?
Yes.
Can you go 1, 2, 3, and then the spacecraft with the Hall effect? Can you just explain that real quick for listeners?
Oh, sure. So there's an old saying which is low Earth orbit is 50% of the way to anywhere in the solar system.
Oh, okay.
So getting off the planet is extremely hard. It's like, that part's tough. But then once you're in space, you have a lot of options for doing whatever it is that you were trying to do in space and go where you need to go. To get off of the planet, you need both a lot of thrust because you have to, lift things out of the gravity well. It is beneficial to have an efficient engine because you carry less propellant. You should all look up a thing called the rocket equation.
I knew that was coming.
But it basically just says you have to carry a whole lot of propellant. And most of your rocket will be propellant. And it's in proportion to the mass of your vehicle. So rockets historically are staged devices. There's a mythical thing called a single stage to orbit, which nobody has ever built an SSTO yet, as far as I know. Somebody out there will be like, no, actually, there's a tiny one that the JAXA built in the 70s or something. Rockets for delivering payloads to space have some number of booster stages. Well, there, a bunch of a bunch of engines will burn, and then typically the bottom part of the rocket comes off, and then some more engines will burn, and you can have any number of stages. Many orbital rockets have 2 stages, booster stage and an upper stage. Like the Saturn III had 3 stages, and a stage is just like, rockets fire in that stage, and then that piece of the rocket falls off. The kick stage for Rocket Lab was a very small third stage, which was mostly for maneuvering around into different orbits, as I understand it. I could, again, like I could be misrepresenting that somehow.
So in that case, the first stage was the booster. The second stage was like the get to orbit. The third stage was like positioning in orbit, that kind of thing. The kick stage.
Yeah.
Third. Yeah. And
so a Hall effect thruster or an electric propulsion system, they all have some things in common. There are many ways to get thrust from electricity and reaction mass, but they all have in common that they're not combusting something. A proper like booster stage engine that uses kerosene and liquid oxygen, you mix those propellants together, you set them on fire, and then the energy in the chemical bonds is released, and that's how you get thrust. EP doesn't burn anything. It accelerates an ion, and so in theory, if you have a big enough power supply, you just keep turning that juice up, and you can get there's no limit. It's not like there's a finite amount of energy stored in the chemical bond, but there's no upper limit in theory to the amount of push you could give to an ion. That is the thing EP people like to say. In point of fact, there are a lot of practical upper limits.
Well, one is you either have to carry it with you or you have to go and capture it from the sun, store it, and then redeliver it, right? That's its own
Exactly.
own set of problems, I would think, right?
Yeah. It goes back to power electronics sorts of problems,
Yeah, listening to you, Todd, basically there was no other path for you than this. I mean, like basically, like everything you've said is like, of course Todd's going to be working in this space.
I
Like,
mean,
how could he not?
You're right. I did call out stuff from Cochrane long before I started this, so yes, it does make sense.
It's good. It's a hell of an arc, you know. Talk about science. It's not even science fiction. It's just science, man. It's just science.
Well, that's the thing too. Is like, and we'll get to the last part of this anyway. So EP is accelerating an ion beam. It's only good in orbit. You typically it doesn't work in atmosphere because of the gas densities involved in it. So it won't operate, and B, even if it did operate at atmosphere, it produces a very tiny amount of thrust. So that's fine when you're in a zero G environment. It would not be fine if you were on Earth.
In moving satellites around as well, I think about other ways that I've heard about, or maybe wrong, but like one is like letting gas out and just the momentum kind of like gas goes this way, you go that way sort of thing, but then you run out of gas, right?
It's a cold gas thruster. It's still extremely useful.
Sure. But like hard to do and like long-term energy density type of things. Right?
Exactly. A cold gas thruster is typically used for maneuvering. You don't usually use them to like change an orbit or do something. It's just like requires a lot of delta V, which is delta V is change in velocity.
What do you think about the book Delta V?
I've never read the book Delta V. What's up with the book Delta V?
Oh man! Oh wow! Daniel Suarez, Delta V. There's 2 books. There's a third book that's on the way.
Okay.
Oh, that's got to go on your list. Okay.
Delta Recommendation? You like
total
those?
recommend.
All right.
Like 100% recommendation. Definitely mentioned it on the show before.
Okay.
I love that book. Yeah.
I will check
great.
it out.
I can't wait to hear your take on it.
Awesome.
Okay. Delta V though, as Delta V is just like the amount of energy it takes to move to a new orbit, right? Like that's kind of the shorthand for it.
It's velocity change. So the amount of energy it would be like impulse, like Newton meters.
Got it. Okay.
Yes. So anyway, EP generally speaking is for use in orbit. But the reason you use it is because although the thrust is quite low, the efficiency is really, really high. So people talk about rocket efficiency and they use a unit called seconds of ISP. The number of seconds of ISP is a comparative measure which says how much mass do you use to go some distance, basically. And a really, really good booster stage rocket engine is around 400 seconds of ISP. And a crappy Hall effect thruster is maybe 1500 seconds of ISP. So even like even like the best to like a pretty mediocre one, it's much more efficient to use one of these EP systems.
And that's because you also have to take that mass to space, right? That's like one of the problems.
Yes. So the reason why it's beneficial to use less propellant is you have to carry it there in the first place, and once you are there, if you're 3 times as efficient, you can do 3 times as much maneuvering.
Right.
So you can if you're maintaining your orbit, you can stay in orbit longer. It limits your lifetime there less. You can maneuver if your spacecraft is into maneuvering, which like a lot of Air Force satellites are into that sort of thing. You can maneuver with in the parlance they like to call maneuvering without regret.
That's a good one.
You can orbit raise. So like a common use for thrusters is to change orbits. So you get dropped off by a rocket in some orbit. It's not quite where you want to go, and so you use your thrusters to get to where you actually want to be.
Right, and also, I mean, don't many orbits, not all orbits, degrade as well? So you have to like kind of like charge it back up depending on like drag and thrust, or drag from the atmosphere and stuff like that if you're in low Earth orbit.
Exactly right. That's called station keeping. That's a very common use of thrusters.
Again, I've learned that one from, I think that was The Martian, they talk about it, and I think maybe Delta V they talk about it too, but it's asteroid mining. It's all about asteroid mining, Delta V.
We've met some asteroid miners in our time.
Yeah.
Cool. They're trying. And I hope for the sake of the sci-fi future that I want to live in, somebody works it out.
It seems like the only realistic way to, I mean, like basically it kind of skips a lot of the boost problem, right? Just to, you don't take stuff to space, you get stuff from space and you drag it back. And like that kind of idea.
So I think, and when people talk about like, what is it going to be good for? There's a company called Karman Plus that is a company that I've like to chatted with a bunch. And their tenet was always like, well, you can haul a rock back from space, but if you want to bring it back down to Earth, you have all the same sort of problems. But really, when it'll be useful is when people need to build things in space. Then it'll be super handy.
Yeah, totally. Yeah, it's really interesting. Really interesting stuff. Okay, so we're talking about satellites
Mm-hmm.
with electric propulsion. So that's the main consumer, is like someone who's like doing a consumer, like a sensor or a radio thing, or a, not like a SpaceX, but like someone like that that's wants to stay in space, so they do space station keeping.
Yeah. So the people who buy Hall effect thrusters or electric propulsion in general are usually people who make spacecraft. So what we would in my business, you would call them a bus integrator, or a bus manufacturer, and that just means people who make or put together satellites. And that's who buys. There's an old saying about circuit design that's like, the analog part is what, like 20% of the circuit and takes 80% of the effort.
Mm-hmm. Yeah, Pareto style. Yeah.
What's that?
like Pareto principle and stuff like that.
Yeah. And there's a similar sort of saying. Well, I don't know if there's a saying, but there's a belief, and again, grain of salt because I'm biased, that in spacecraft there's a disproportionate amount of agita that goes into the power and propulsion systems compared to what the spacecraft's actual job is doing. Like, no spacecraft goes up there and is like, we're just going to zip around and do nothing. They're always up there to do something, which is what they're
hang out, not make any money.
Yeah. Just do laps.
Right.
But the generating power and getting from place to place is because they're relatively complicated subsystems. They do sort of suck up a high degree of like thought and money and effort on the part of people who are putting satellites up.
And the culture is to buy, not off the shelf, but like buy systems that are already proven and then reuse. That's kind of the idea.
Depends on who it is, right? So like some people make their own. SpaceX famously makes their own Hall effect thrusters. So they build an Argon thruster, and all the Starlinks have one, and they build it. Most other companies, I think Kuiper, which is Amazon's constellation, is in theory building their own thruster system. Rocket Lab just was like, what we really need is a Hall effect thruster.
We should call Todd. Yeah.
I tried to get him on the phone and be like, hey, you want to buy one from us? And they were like,
right.
Take a walk, Todd.
Right.
But many companies, especially companies that build like, fewer than thousands of satellites, typically buy really specialized components. So like a lot of people make their own torque rods, which is basically a big electromagnet, which is used for, if you're if you've got a satellite in orbit, you can energize magnets in it and use the Earth's magnetic field to give you different pointing.
Oh, cool. Okay. I didn't know that.
I
knew there was like reaction wheels. I remember when Sean was on the show, he talked about reaction wheels a lot, but I didn't know it. I don't think torque rods were on the list.
Torque rods are so much more benign than a reaction wheel. Like, you can't always use torque rods because you have to be close enough to the Earth for them to be useful. But God, they're like simple and like it's nothing to break. My 2 cents. If you can use a torque rod, if you can get away with using a torque rod, use a torque rod.
Sure.
They're an example of like a relatively simple space component. So people often buy those, but like, or people often, it's a good, in the trade space, people are more likely to make that because it's not that hard. But like a propulsion system is esoteric and it's hard to test, ostensibly dangerous. And so like people tend to purchase those if you make less than some number of satellites.
Yeah, it kind of sounds like, I don't know, like, well, I work in cloud space now too, but it's like people buy, kind of cloud component. Like you could engineer everything from the beginning, but like if you're not big enough and you don't have the requirements for it, like why would you, right? So they buy off the shelf, small, medium businesses do that sort of thing. So that makes sense to me. Also, like, they would never get to space if that was the case, right? I mean, like just like tiny satellite companies aren't building their own rockets too. They're hitching a ride. It just doesn't make sense. There's still cost basis, but it's not massive. So did Apollo actually get to the point of making this thing? So you had this.
Yes.
So okay. So Mike successfly pivoted. Yes.
Mike Cassidy successfully pivoted. After that, I got hired to help out designing power electronics, and worked with Alex, from Astra. Worked with my old buddy Mike Schmidt back from Lockheed and Calvin Klein Doors. It sort of like brought everybody along. Built a totally respectable piece of space power electronics to run this thruster, and we flew one, and we flew exactly one. And then our company was acquired, and they were acquired by Astra Space. Wah, wah. So which was, there were many good things about that. It was a successful exit to Apollo Fusion, good for a lot of people. And, Astra took on that product line and will still sell you a thruster to this day. I, had already worked at Astra and as this show should be pointing out, was mostly interested in building something new.
So to quote a great philosopher, is going to be a no for me, dog. That's what it sounds like.
Well, I mean, when that happens, when your company gets sold, you're kind of a schmuck if you leave right away.
Yeah, there's money on the table for sure. Yeah,
there's money on the table, and also like it's bad look.
Oh, I see. Okay.
To just be like, thanks for the money, I'm out. So Mike, being a good boss, did a pretty good job of retaining his team for long enough for me to be like, all right, I and my team will get the PPU, the piece of power, the power processing unit, the piece of electronics, to a point where it's like reproducible enough that you should be able to crank them out, and they're sitting here ready for our first customer, and then I'm going to split. And so that's what I did.
Got the job done. That's important.
Mm-hmm.
So then you split. So what was after that then? So then that takes us almost to a couple. This takes us to the point where I think I started getting emails from Todd at Starlight Engines, I believe, right?
That's correct.
Which were some of my favorite emails. I really liked that you did that. I don't know when that started, but it was great.
It was a chance to use your own voice, right? Like I could be as weird as I wanted to be, because it was my sandbox. So at that point, right, like Apollo had sold, I'd worked on electric propulsion. I had done the thing which I had sort of set out to do. And, the ACE thruster system, the Apollo Constellation engine, was a good thruster. It was a good thruster. It was a great team. It was a good experience. The electronics were good. So, I was like, well, what am I going to do now? And I had only been at Apollo for a short time. I was at Apollo, I think, for a year. And then, after we were acquired, I think I was around for maybe another year after that. But it was pretty short. Now I had worked on electric propulsion, but now I had all these opinions about electric propulsion. And I was like, oh, man, wouldn't it be great if? So there were a couple things that when I was thinking about what I wanted to do next, I was like, I want to build something which is like not the warp drive, but like 25%.
Not yet. We'll get there.
Not yet, but 25% better than like what's out there now. Like footnote in the history book. And then in this year, these people made this novel change to electric propulsion, and it mattered. And 5 years later, somebody else made something that was better, and then it wasn't.
Wikipedia footnote, at least, yeah.
Wikipedia footnote. Actually, what I really wanted is I wanted to be mentioned in Goebel and Katz's Fundamentals of Electric Propulsion, which is the textbook about this. That's what I really want. So if you're out there, Dan Goebel, Scarlet Engines, okay. Holler at me.
Goebel and Katz. We'll I'll have to take a look at that. I've never read a book like that, so that's
it's a good one. Like there's esoteric textbooks about almost everything, and sometimes they have information, and sometimes they're fun to read, and very rarely are they both fun to read and have useful information.
Oh man, I still remember my textbook on plasma physics from my dry edge days, and like, oh man, what a great way to fall asleep. Just like the best. Except for the heft of the book as it slams you in the face. As you fall asleep,
The Debye length. Yeah, totally. So I had opinions about like, wouldn't it be great if you could make a marginally better, because a lot of the time, like in commercial space right now, there's a long history of like stuff that has gone to space, but now there's all this like there are more satellites in space now than there ever have been, and that number is going up all the time. There really is a need for things that there didn't used to be a need for. And one of those is like, propulsion that doesn't take like several years to build and doesn't cost like a gazillion dollars. And so I was like, I think that's what I want to do. And so you start looking around, and there's only one place that I was interested in working. And that was a place in Massachusetts called Busick. All of you should go buy a Busick t-shirt right now. This company has been around since the 80s. If there's an electric propulsion concept out there, they have tried it at least once. They're like a family-owned company. I don't think they have taken any venture capital. They've published 1 million papers, and it's like they've been at it since before it was cool. And they're a hugely important part of the electric propulsion community. And it's run by a guy named Vlad Ruby, and his son Pete now helps him run it. And it's like all the sort of things that it's like a real good guy, success, America doing the right thing, capitalism working kind of like story. And so I interviewed there, and it was cool. And they were just as cool as I expected them to be. And they were really wonderful. But I wondered, space is slow. Getting things into space is hard. It takes a long time. The things that I worked on for Lockheed, I'm not even sure they're on a submarine yet. Like sometimes these worlds, these worlds like like can be slow moving. And I don't know if this is true or not, but I really wanted to be able to get something done quickly. And I had just had this experience at Apollo where, I'd watched this really expert CEO like really pull off a lot of stuff really fast. And I was like, well, what the hell, man? I'm like not as young as I used to be. Like if now's the time, I'll try starting a company. So one of the other guys from Apollo, Mark Hopkins, and I co-founded a company called Starlight Engines with the concept of making a new type of Hall effect thruster system. We started in June of 2022. We received our first funding in August of 2022. And we developed the first commercial metal propellant Hall effect thruster system. So we use a zinc propellant, which has been done in the lab before. Busick certainly have done it, but no one's built a system which is flight ready. Part of the trade and figuring out what to do was being like, all right. I am like well versed in like you can make a clever thing, and if no one buys it or it's the wrong thing, like you're done. And we settled on zinc and this type of Hall effect thruster system, not because it is not the best propellant that you will ever encounter, right? Like xenon, the traditional propellant, like xenon is a traditional Hall effect thruster propellant. It's an amazing propellant. Zinc is not quote unquote better in many ways, but you know what zinc is? It's solid. It's solid, which means you can pack it more densely than any dumb gas. It cannot leak, and it costs $4 a kilogram.
There it is.
And so it's like all of a sudden your supply chain doesn't involve like stupid like orifices and clean rooms and like valves that are made for 4,000 psi noble gases that take 18 months to get, and they're only made like by one company. Like,
right.
Like
you're arguing with fabs to get it so that they don't use it up, and there's only a limited supply.
And no one's gonna. You're never gonna win against a fab. Like there's like actual money there, right?
Right. TSMC is big.
So we were like, no, man, like this is the like Honda Civic of Hall effect thruster systems. It has a lot of great, like it's zinc is relatively light, which matters for its atomic mass is lighter than xenon by a lot. And what that means is it favors efficiency over thrust, which most people want more thrust in this world. But there are some other good things about it too. Like it's a metal, so it's easy to ionize. The hardest part is obviously all of the other propellants typically are gases, and so you have to make zinc into a gas before you can use it as a propellant. So there's these significant engineering challenges to overcome, but the reason why it's beneficial is because it's a system level advantage, right? Like it's this thing that can't leak, that you can leave on a pad forever and nothing bad happens. It's like a hydrazine thruster will totally mess you up real bad if it has a leak. Like, you can you shouldn't lick the zinc a lot before you put it in the thruster, but if you did, probably nothing bad would happen. So there's all these,
lickable.
It's
lickable EP. You got it.
So there's all these like advantages where it's just like, it's easy to use. It's cheap. It's dense. And the performance is better than a lot of the other cheap propellants, right? So like SpaceX pivoted to use argon. Argon is another noble gas. It's a cheap noble gas, but it is like hard to get good performance out of argon. It's not as hard to get good performance out of zinc, but you have to solve all these engineering problems where you have to, make zinc into a gas, which is a pain. But we were like, no, we can do it. And
so I know I shouldn't do this 85 minutes into the amp hour, but what do the electronics look like for something like this?
All right, so your viewers can't see it, but this is one of the PPUs sitting on my bench right over here.
Cool. Block diagram, I guess. Really, I mean, we're not going to get into. Pure circuits,
so there's a processor, there's a communication section. Ours talks RS-422. Housekeeping supplies and whatnot. There's a lot of circuitry associated with that solid metal feed system. And then the main thing that EP nerds will talk about in the electronics design is the discharge converter. And the discharge converter is the power supply that runs the ion beam. And so that takes up a big part of the board real estate, and involves custom magnetics. This is my first planar transformer that I've ever designed. And that was really fun and great. It's throttleable, this design. So, right, like if you're into power supply design, efficiency is the thing that everybody sort of chases. Our system's throttleable from 300 watts to 800 watts. Really, the converter will go down less than that. And it's a 28 volt spacecraft bus, and the discharge converter can run anywhere from 250 volts on down.
So in my head, I'm thinking about like a CRT, like you're basically thrusting this. It's not electrons, so it's heavier stuff, but it's like there's something that's kicking this stuff out the back, and then you're steering. Do you steer the beam, or you just contain the beam?
You just you contain the beam, and that's all done with magnets. So
got it. Okay.
So yeah, also like a little bit like a CRT.
Yeah. So ions have charge, electrons have charge, right? Yeah. Yep. So that's how you kind of keep it without going off into every direction. It goes within the direction you want it to, which is out the back part, right?
Yeah. We talk about people in EP talk about plume divergence. How much of your plume goes in a straight line out of the back? It should be quite a bit if you're doing a good job.
Okay. Okay. So what actually makes it go in the first place? Like what is pushing the ions out? So you have to make ions first, and then you push the ions out. Like what is it?
Exactly. So you so you start. In our system, you have to get from a solid to a gas. Most Hall effect thruster systems, you start with a gas already. So it's a neutral gas. It comes into the thruster. Thrusters have an anode and a cathode. The cathode is a thermionic emitter of some kind, usually. Just like the cathode, it's historically
a tube
barium.
amp.
It's just like a tube amp, right? Like it's a barium oxide. It's barium oxide in a lot of designs, and it's Lab 6, lanthanum hexaboride in a bunch of other designs. But there's an electron donor, which is the cathode, and then there's an anode, and then in a Hall effect thruster there's a magnet. And so you'll heat up your cathode, or you'll make your cathode emit. Typically, it's by heating it up really hot. It will, as they say, quote unquote, boil off electrons, and they'll get caught in this magnetic field that you've generated in your Hall effect thruster. Then you release a neutral gas. The neutral gas will flow through this area of high electron density, and as it goes through that area of high electron density, there is some high likelihood that a neutral gas atom, which is not moving all that fast, will collide with one of the electrons. It will knock an electron off of this neutral gas, and it will become positively charged. The location in the thruster where that is most likely to happen is really close to a positively charged plate. So when that neutral turns into an ion, all of a sudden it feels the push from that positive plate, and it's ejected out.
So it's basically like a tennis ball shooter. The tennis balls are all kind of bouncing around in the hopper at the same time in order to get ready to shoot out the back or something.
Yeah.
Like, no, that's not how that's not how it works, Chris. Todd, can I work in EP now? Can I?
It's notoriously
I'm a communicator, Todd.
It's like if you have a cloud of tennis balls.
Okay.
And you're sitting like near them with a magic wand, and you point at one of them, and then like that one goes really fast.
That one goes. Okay.
Yeah.
So probably tennis balls was a bad starting point. Huh. So So the novel part is first that you're starting from solid and making the gas, right? Yep. And but then is everything else kind of the same then? Like they're just feeding gas in, but you're making gas and feeding it in?
That's the hardest part of it. Yeah, the hardest part of it is the novel propellant, and that's the sort of the biggest differentiator. Now, I think we happen to do a lot of other things really cleverly, like
of course.
The sort of like electrical isolation in the thruster head is like good for us. Like this, we survived really high shock and vibe levels, which was hard to do, and that took a lot of engineering work. The throttleable design, I'm particularly proud of. Like most of the time, a lot of these thrusters will be a 400 watt thruster, and what it means is that you can only sell it to a bus that has 400 watts. But some people will be like, I got 300 or 350, or man, I want twice as much thrust. Is there anything you can do? So you can use it on more missions if you can make it throttleable. So designing the power supply to do that was I was proud of that. Some of the heater design is novel. So I do with it. There's some incremental improvements, but the one that matters the most is the propellant.
Does Starlight care about the collection and storage of power in the first place, or is that up to the people that you're selling to, like collecting from solar, storing in batteries or some other mechanism, and then delivering that power to the EP?
We don't build anything to do that. I mean, certainly because of my background, and certainly because we are often one of the largest consumers of power in a spacecraft. It benefits us to be savvy and think about that sort of thing, but we don't sell batteries or anything like that. We thought about it. There's not a great business case for selling space batteries.
Sure. Okay.
But I'm eager to be proven wrong on that.
Okay, cool. I mean, are there other sources as well? So like solar feels like not easy, but easier than like a RTG? No, what's
RTG.
the RTG? Like the RTGs I read about are going away because it's like the plutonium they need for is harder to get because of nuclear arms treaties. But RTGs can also generate power
Right.
and then deliver it. But like, is there a benefit? Like, do people choose between them or no?
For commercial missions, solar is kind of the only game in town.
Okay.
So getting an RTG into orbit requires like the president to sign something. Like it's like
Okay.
it's
That'll do it.
it's flying nuclear anything is tough. Now there's a big movement in space right now to fly nuclear reactors.
Got it.
And if you're a propulsion nerd, you're probably into that because it opens up all this kind of propulsion, which was not feasible before that reactor is up there. But for commercial missions, it's always solar.
Got it. Yeah, I mean, I think about it just like if you wanted to go somewhere very, very far away, you could have a little bit of acceleration for a very long time, but you can't do that if you're farther and farther away from a star. So,
right.
Yeah, nuclear would be important, I feel like. Not that that's what people are doing here either, but someday when the fusion reactor comes up, Todd, you're gonna have to do this. So
I would love to. I would love to be at a point in my like Silicon Valley career where I can be like, I too will like try and save the world because I've done everything else yet.
To make the world a better place. To make the world a better place. Yeah.
I don't know. I mean, if you're gonna get competitive with your rich buddies about something, like saving the world's like you could do worse.
Yeah. Well. Yeah. Okay. So it works. I mean, like that's the punchline here. You got what was the getting over that hump was that solid fuel to making it gas and then using it, like, or was it just kind of getting everything together and making it work at all?
Early on, before we even got funding, we like ran some tests to make sure that we weren't diluting ourselves. And so, pretty early on, we became, as far as I know, the first thruster system that ran every bit of it on a solid metal. And so that worked. But no, making a thing flight worthy is really hard. That's probably the most challenging thing, right? Like building a thing that will like survive shock and vibe, that you can like stick a screwdriver in the output of any of the various like, and that's like a thing. I have a screwdriver that's sitting over there. It is the like final acceptance test screwdriver of being like, when you build a power supply, you jam the screwdriver in the output and you put it on the scope a bunch of times and you watch what the recovery looks like. And then you should expect it to pass all of its tests again after you've done it.
Wow.
Designing it not just for space, but for the fact that like it's gonna live a life before it goes to space and like, to survive and make it through all of that is the hardest part. And for us, the novel propellant system is both like I've built electronics before, Mark has built thrusters before, but nobody's built the feed system and the vaporization system like the one that we've built. And so that's the one that's full of like surprises where you'll be like, we didn't know that before because I don't know if anyone knew that before. And it's what makes it fun too.
Yeah. I mean, I can imagine there's an additional, despite raising funding, it's not like startups have access to all the things that like a SpaceX have started, access to and all that sort of thing. So you have to, that scrappy factor is also, I'm sure, a huge piece of getting this thing off the ground.
Oh yeah. I mean, our first thruster was our first cathode looked like a Home Depot plumbing pipe because it was a Home Depot plumbing pipe. There's a hollow cathode inside of it, but the structure of it was like a gross iron tube.
Nice.
And yeah, like we built a vacuum chamber that would get down to, Mark really built a vacuum chamber that would get down to 10 to the -5 torr for like $15,000, which is that's unheard of, right? And it's because he carved it from a tree and because he's done it a million times, So it's certainly scrappy, and that part's fun too, right? Like if you're like,
sure, yeah. That was my favorite parts of the newsletter you sent out. I mean, I don't know how I got on the mailing list, but I was sure glad I did. And then eventually seeing the purple flame that you shared as well, that was super cool.
It's plume, not a flame.
Jeez. Oh boy. Okay.
Haven't you been listening? There's no combustion.
Jeez.
It's not a flame.
Got it. Well. Joke's on you. I don't know how flames work either.
I don't know how they work either, but I'm pretty sure it's not.
What do I look like? A chemist? Some kind of caveman? Yeah. Oh, wow. That's really cool. So you guys built your own chambers, you tested it, that sort of thing.
Yep.
I mean, throughout this whole process, Todd, I believe I asked you probably 85 times to come on the show.
Yep.
And you're like, I can't yet.
Yep.
And then finally, you sold the company, and you're like, yeah, now I get to, which is great.
And now I get to.
Yeah, I was very excited about that. But like where is it in the going to space? Like, what is is it up there yet?
No, it is not up there yet. It's so
okay.
that's like
well, I mean, That's its own thing, right? I mean, like you said, we've already set up the stage for that. It's not like it's an easy thing, flying in space.
No, it's not. I mean, it's part of the job is when you make a novel thing like this is to try and get someone to believe that you're not a quack. And it helped that we built this other thruster system before that totally did work. Then it's to get somebody to hopefully buy one of these things before anyone else has flown it. Which, our policy was always just give the first one away.
Oh,
like it's where you're like, just get it up there and functional. Like the amount of credibility you get from having a system operational in space is so great that that it's worth whatever money you lost to make one. So we've sold a total of 4 of them for whatever reasons. They're like, we've sold 4, we've delivered 2 kits, and neither one of those, I don't think either one of those has been to space. We actually wouldn't necessarily know if they had been.
That's its own thing. Yeah, it's its
own thing.
That's like DigiKey doesn't get to know where the parts go, right?
Exactly.
They know the shipping address. They don't know the end result of if it's in the remote they're holding in their hand at the end of the day, right?
Totally. So I mean, what we can say is that we delivered them to customers.
Yeah, right.
After these 4, we had a company come around, and it's cool. It's really a small world in some ways. Like, we knew some of the founders from this company and had met them a handful of times before, and had been badgering them to buy engines from us, and they were like, yeah. And then this company, they're called Muon Space. They're good engineers and savvy people and decent human beings. But they had their own stuff going on, and they weren't interested in our thrusters early on. And then something happened, which, read they had thruster problems. Sure. And then they got really interested. And then, we started talking, and it was cool because they were not put off by the fact that we were 2 guys in a garage and a handful of contractors. They were into it, and they were like, we had the exchange that was like, well, you could buy these thruster systems or you could buy the company, and they chose to do that. And that process, let me tell you, if you had another hour and a half, let me tell you about going through that. That's a gray hair inducing process.
It's a roller coaster ride, so I hear. Yeah.
And it really is crazy. Being. So I was officially the CEO of Starlight Engines. Now, Starlight was not a big company, and it was a deeply technical company with people who I'd worked with previously. So you'd think, how different is that from being, being a tech lead at another company? And the answer is, it is so different. It is so different.
How many lawyers have you talked to in the past couple of years, Todd?
We had, a lot, but Starlight had a great lawyer. I came out of this process with such superhero admiration for our legal counsel. Her name's Rachel Paris from DLA Piper. Anyone who needs a fabuless, extremely expensive lawyer for corporate M&A, you could do a lot worse. She was amazing. Yeah, but the process is crazy, and it's not like engineering.
There's no straight lines. A to B, go, put in more work, get more. Well, I guess they put in more work, but there's a lot of emotional roller coaster, I'm sure.
Yeah.
Well, at the end of it, you did sell, and that's great. Congrats. But the job ain't over. So now what are you going to be doing at Muon? Or what does Muon build, I guess?
Muon builds satellites.
Okay.
So, cool. I'm probably misrepresenting them in some way. They would use, their marketing team would use, more complicated terminology than that.
Sure,
they sell systems. But mostly, I think the part that the people really want, right, is the part that goes up to space and, does stuff. Muon is probably the most famous right now for building fire detection satellites. So they built a payload which is good at scanning different types of infrared and collating that data in such a way where it's quite good at figuring out where fires are in the world, and which was both relevant and super useful, primarily sensing payloads. So they're kind of the good guys. They have good leadership.
Yeah,
it was they really need thrusters, and it was that process I think can go really south, and time will tell how the long-term relationship goes, but so far I'm pretty optimistic about it.
Well, I'm really excited to see last time I had a 12-year ago guest on a similar kind of journey of wow, I can't believe you got to where you are now. And I'll say the same thing, let's not make it 11 years, but wow, 11 years from now, who knows what you're going to be building, Todd. So I have to assume fusion engine, fusion warp drives rather. Sorry, warp drives.
Yeah, I wouldn't have known then, and so yeah, I think it's fair to say I don't know now.
Where can people find you, Muon? Your Starlight stuff. Is that stuff online somewhere? People can look it up.
Our old website is very vaporwave and has some cool pictures, but not a lot of useful information. But Starlight Engine
has not persisted, but I enjoy it. I enjoy it.
It hasn't. But if you want to blast from 5 years ago, StarlightEngines.com is like a picture of some of our stuff. Okay, Muonspace.com is where you can find Muon's business. They're in Mountain View, California. They're a great company. Okay. If you're trying to get into space, you could work at way worse places than Muon. And for me, I'm actually not really on social media much anymore.
Yeah, same.
But I am on LinkedIn.
Business, huh? Yes.
Yeah, I don't know.
That's great.
If you ever want to, anyone who ever wants to talk electronics, that's usually what sort of like
that'll grab your attention.
I'm always happy to answer electronics.
Yeah. Great. Yeah, I'm sure. As you build more EP, you'll need more plucky young engineers that you can mentor as well. So that'll be great. Hopefully, some of them listen to this and come work for you and build the fusion engine of the future.
For sure.
Sorry, I keep saying it's fusion engine. It's warp drives of the future. All right. Well, thanks, Todd. Thanks for being back, and we'll chat soon.
Thanks, Chris.